Hi everyone. Um, so we'll be doing the second video to actually prove that the bases of a one form are linearly independent. So on the first video, we showed that the bases of a vector are linearly independent. For this video, our aim is to show that the bases of a one form are linearly independent. So we're still going to use the same technique that we used from the first video, using proof by contradiction. As I mentioned earlier, this is the most commonly used tool in mathematics, proof by contradiction, to assume something which would be opposite from the statement that you are trying to prove, like from the theorem that you are trying to prove, and then disprove it, like supporting yourself using rules and stuff, you know, or previous statements that you have encountered. So now we're going to deal with the one form. I won't be deeper as from the vector, because with the vector I was trying to be more deeper, because you are not used to the definitions, like what is a vector, what is an nth dimensional space, and etc, blah 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 blah. But in this particular video I will try to be as short as possible as I can, but trying to prove that the bases of a one form are linearly independent. um I think we can start doing this proof. Yeah. So we are required to prove that the bases of a one form are linearly independent. So we are required to prove that um, the bases of a one form are linearly independent, are linearly independent. So we are required to prove that the bases of a one form are linearly independent. I think I must change my pen because this one is not very clear. So if we are saying that the bases of a one form are linearly independent, we are actually saying that all of its components are equals to 0. Same as from the vector. Okay, we're going to prove this using proof by contradiction, as I've mentioned. But let me just show you a one form in that Einstein summation formula. So a one form is represented like this: double A dxa. You choose any symbol that you like, but be careful of these indexes. You don't want to swap things around, like putting this A on top. The correct version, they say when you chose that funny W sign, oh, it's not a W in fact, that funny omega sign. So be careful, it should be like this. So if we are saying, okay, these are the bases of a one form, and this is the components of a one form. So if we are saying that we are trying to prove that these bases of a one form are linearly independent, we're actually saying that all of these bases, all of these components for this basis should be equals to 0 in order for these bases to be linearly independent. Let me just try and expand this Einstein summation. So this Einstein summation is something like this: double 1 dx1, it's omega 1 dx1, omega 2 dx2, plus da 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 omega n dxn. I think I must write it. It's omega 1 dx1 plus omega 2 dx2 plus da 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 omega n dxn. Okay, this is basically an Einstein summation. Don't worry about this because you saw it from a vector. So we're going to prove this using proof by contradiction. So let's assume to contrary that the opposite is true. So let's assume to contrary that the bases of a one form are linearly dependent. Remember, from the statement we are trying to prove that these bases of a vector are linearly independent. So, but I'm saying that let's assume to contrary that they are linearly dependent. Let's assume to contrary that let's assume to contrary that the basis of a one form funny omega are linearly dependent. So if we are saying that these bases of a one form are linearly dependent, we're actually saying that all of these components, okay, so if we're saying that these bases of a one form are linearly dependent, we are saying that at least, sorry for my initial statement that I've made, so at least one of these components should not be equals to 0. For the initial case, when these, from the above original statement, when this one form is linearly independent, it means that all of these components should be equals to 0. But for our case, when we have assumed that these bases are linearly dependent, this means that there must be at least one of these these omegas, these components for this one form, to be not equals to 0. Maybe double 2 is a number, the rest could be equals to 0, but at least one of them should not be equals to 0. So this implies this, that there exist at least one double k not equals to 0, ne? In order for our one form to be linearly dependent. So, as from the first video, we saw that a vector, it is a differential operator that is acting upon a function, So also the one forms, they are operators that can act upon a function. But in this instant, we're going to choose our one form to act upon the basis of the vector. So let our one form omega to act upon the basis of a vector. So we want our one form to act upon the basis of a vector del by del xk. So this is our one form in that short notation, and these are the bases of the vector in which our one form will be acting upon. Um, so our one form is acting upon the basis of that vector. So this is our one form. Let me try and zoom this. Del by del xk equals to 0. Our one form is acting upon the basis of a vector. Let's replace this omega with the original Einstein summation of a one form. Del omega a del dxa del by del xk equals to 0. So applying linearity here, this can come out this omega, and then we can be left with the basis of a one form acting upon the basis of the vector. As the same thing will apply from the first video, this will give us the Kronecker delta, but things tend to change a little here. If you saw the first video that I did to prove that the basis of a vector were linearly independent, you'll see that there's bit of a change, but we're still applying rules. It's still okay. The Kronecker delta is still the same. We are not breaking rules. Remember, in maths we are sticking with the rules. Whatever you do must be supported by the rules. So I'm using the rules. This basis will turn into a Kronecker delta. Again, we'll apply the duality theorem for the Kronecker delta. If A is equals to K, then this implies that our Kronecker delta will be equals to 1. Then everything here for this basis will be equals to 0. Now, if A is not equals to K, this implies that our Kronecker delta will be equals to 0 and everything will be 0. Okay, let's take for the first part of Kronecker delta for A equals to K. This implies that our basis del K is equals to 0. Not basis, sorry, these are not bases, these are the components for the one form. Now we can see that all of these components for the one form are all equals to 0. From our initial statement, we assume that the bases of a one form are linearly dependent. And we mentioned that if the bases of a one form are linearly dependent, there exists at least one of the double k's, the omega k's, which means the components to be not equals to 0. So this implies that from this Einstein summation, there must be at least one of the components for this one forms. You can call W, but it's not W. These are the omegas to be not equals to 0. So we have proven using proof by contradiction that all of those components are all equals to 0. And we can say that our initial assumption was wrong. Hence, using proof by contradiction, we have shown that the basis, this basis of a one form are linearly independent. Now you can write your conclusion here. So, hence, using proof by contradiction, we have shown that the basis of a